All right, so we're looking at a second midterm. Be on Monday, the 25th, I think it is. And that'll start on chapter 9, I believe, which is Q equals VA and flow and that kind of stuff. And then it'll go through chapter 12, which the homework for that is due either today or Wednesday. I'll try and get that homework turned around and getting it back to you soon after you turn it in, whenever that is. So we're talking chapter 9 on page 86. And that's going to go through chapter 12, which is the stuff on minor losses. And that's page 124, actually. It's 124. Okay. So that's what will be on that midterm. Okay. So what we're going to cover here today won't, but all the same, we'll cover this, of course. All right. And I'll get you a review for that on Wednesday. All right. Okay, let's look at piping systems here a bit. When you put a water distribution system together, you loop it, is what you do. You don't want one flow path to a location if you can avoid it. All right, so if, let's say we've got a house here, and we want to see how this house gets its water, it could come around that way, or it can come around that way. See, and that's a good thing. That leads to much more efficient flow of water if you loop the system and tidal together. Yeah, question.
How does the flow work with that?
The flow works on the water follows the path of least resistance, and it balances out based on the resistance it encounters. Okay. All right, so this, and this is kind of an issue in any sort of city. If you look at the water distribution system, it's put together in a series of loops. Okay. Now, if you have now, of course, sewer is not. There's no reason to do this with sewer. You just want sewer to flow downhill and access each lot once. That's all you got to do. But water, you really want to loop it through. It makes for more efficient flow. And also, let's say we've got a break right here and we have to shut that line down. Well, we can still have a path to get the water to a customer if there's more than one way to get the water there. Okay, so it's a more efficient way to do it. Okay, now this makes for a little bit more challenging analysis, but what you do is you look at the intersections, which you can call nodes. Okay, and you basically, what you look at doing is balancing the energy for the different paths the water could flow. So here I've got a little example where we just got a real simple system where there's two ways for the water to flow from A to C. What's going to happen is it's going to balance out. So the head loss, ABC, will equal the head loss around ADC. So the flows will balance out such that the head losses equal each other in two possible routes. That's how it works. Okay. So that's how the flows work themselves out. So what you're going to have here, you got Q in equals Q out, of course, because what flows in will be flow out. So I've got in and I've got out. And what that's going to equal is Q ABC plus Q ADC. So that's the basics of it right there. Is the flow in is equal to the flow out, and that is equal to the sum of the two flows in the two possible directions. And the ABC and ADC will balance out so that the head losses equal each other. And that's basically it, okay? Okay. So that's the idea. Now, really, all you do on this
is guess and check, okay? You kind of guess at what the flows are. You do some head loss calculations. You see if they equal each other, and if they don't, you adjust your guesses and run it again. That's really about all there is to it. There's more formal ways and more informal ways to do it. There's actually a formal method that, might look something like that on page 129, where you're making a series of successive guesses, adding up total head losses for different branches, and then based on those results, inputting that, adjusting your flows, and then running another series, and then running another series, et cetera, okay? And you can just keep iterating that over and over again. Now, when I look at something like that, especially a page like that, where they're looking at different data about the system, they're looking at the flow, coming up with the head loss, coming up with the total head loss and all that, that sure looks a lot like a spreadsheet, doesn't it? And see, that's how this stuff would be analyzed, is with something like a spreadsheet. And you would just take your answer and plug it back in and adjust your initial assumptions based on the head losses you get, run it again, run it again, run it again, okay? And I've seen a graph once where they had a computer do this, okay, where they had the flow, let's see, they had the number of iterations of a computer program that analyzed the system, and then it had the cost. And they just put in size of the system and what the parameters were, and they had it calculate all the head losses and then adjust and adjust and adjust, and the basic graph did something like that, where it started off pretty steep, and then as the system got better and chose the lower cost alternatives and started to work with those, the cost dropped pretty precipitously. After a while, though, it kind of leveled out. That was kind of the deal, okay? So this stuff a lot of this is done on computer now. It used to be there were people who kind of specialized in this, put together complicated systems and made reasonable guesses based on their experience, and maybe did 8 or 10 runs of it. But it was just so labor intensive, they can only do so much. Nowadays, of course, we got computers that can just kick this stuff out. So they just randomly put together their first best estimate, run the numbers, and just keep running around and over again. And the goal here would be to reduce the cost of a system that will deliver flows to different locations. That's the goal, all right? Now, I don't want to belabor this too much. I just want you to kind of understand the idea behind how you would do this, okay? So let's just have a look at one example on page 128. So let's say we've got 500 gallons per minute coming into the system. And of course, that means we're going to have 528 going out. And let's just, so we got, 500 gallons per minute coming in and 500 going out. I don't know, let's guess at what we think these might be. Okay, what do we got? So from A to B to C, we've got 1,000 feet of 6-inch, then 500 feet of 4-inch. From A to D to C, we've got 800 feet of 6-inch and 200 feet of 4-inch. Okay. So it looks to me, which side do you think will get more flow? I'm on page 128.
I'd say the A, B, C.
Yeah, because it's shorter, right?
Yep.
It's a shorter run, so that's less head loss for a given flow. So more of the flow should go that way. Okay? Less of the flow should go on the longer run, because they balance out on head loss is what they balance out on. All right, let's just guess about 320 gallons per minute here. If it's 320 from A to D to C, what would it be for A to B to C? If the total's 500? We got a total of 500. We're guessing 320 goes from A to D to C. So that means we're going to have 180 from A to B to C. You all with me there? Then the two will add up to be 500. That's just a guess. I don't know if that's good or not, but let's find out. Okay. All right, let's find the head loss in these different types of pipe now. That would be the next thing to do. So what do we got there? We've got both 4-inch and 6-inch. Okay, so from A to D to C, we've got 4-inch and we've got 6-inch. So for the 4-inch, we're looking at 320. 4-inch pipe, 320 gallons per minute. Looks to be 10.46 on page 108. So 10.46. And then 6-inch for 320, I'm getting a 1.45. So what I'm doing is I'm looking at the pipe and I'm saying, okay, 4-inch pipe, I'm guessing 320 gallons per minute. 6-inch pipe, I'm guessing 320 gallons per minute. Right there and there. Okay? That's all I'm doing. We're good? Okay. Okay, so 6-inch pipe, or we've got 800 feet of it, right? So 8 100-foot lengths. 4-inch pipe, we got 200 feet, so 2 100-foot lengths. It's 20.92. 8 times 1.45. 11.24, so I don't know, let's find out. So 1.45 times 8. 11.6, because that's the lengths of the pipe. What I'm pulling off of the head loss charts is the head loss per 100 feet. The 4-inch pipe is 200 feet long, and the 6-inch pipe is 800 feet long. So that's why I'm doing that. So what I'm getting there is 320.52 feet long of head loss. That's if it goes from A to D to C. Okay. Now I'll do the same thing from A to B to C, but what I have there, I've got a different flow. I've got 180, okay? Okay, so for 180, what do I got for 4-inch?
3.61.
361, okay. And how about for 6-inch? It's probably going to be too much, is it? 0.50? Okay. 6-inch. There we go. Okay. Now, how much do I got? For 4-inch, I've got 500 feet. And for 6-inch, I've got 1,000 feet. So what I got, if the water goes from A to D to C, if that's 320 gallons per minute, I got 32.2 feet of head loss. And if I go from A to B to C, I've got 23.05 feet of head loss. Okay. Now, those are not equal, okay? I don't think I guessed quite right. I'm in the ballpark, they're close. I mean, they're not horribly far apart, but that isn't how the flows are going to be. Okay. So what I've got too much head loss on the ADC side. Okay. We're good with that? So how would I adjust the flows? What's that?
Speed it up.
Yeah, more flow on the, which side, the ADC?
ADC.
Yeah, right. I want more, try another one with more flow on that side, okay? And just do it again, okay? And that's really all you do with this stuff, okay? Now, a computer in a real system is going to do this a lot faster and for a lot more complex system, but this is just the idea, okay? You just balance out the head loss. So I don't know, what do you think for ADC? Anybody got a guess on that side? We're at 320. We got to go down. 3, okay, 300, good enough. And there's no magic answer to this. You just guess and you just see how.
Some arbitrary number that you just kind of go with.
What's that?
It's just like some arbitrary number that you kind of go
You
with.
guess and you adjust. You just keep adjusting based on what answer you get out of it. So 300 gallons per minute, and we got 4-inch and 6-inch. And then we got 200 gallons per minute on the other side. We got 4-inch and 6-inch. We just try again. Okay. So 300 for 4 and 6 looks to be 8.17. Nope. 9.28. There we go. And then 1.29. And then we're going to go 200 on the other side. That'll be 4.38 and 0.61, I think. All right. And we try again. So 9.28. And 1.29. It's 18.56. And what do we got there? We've got 1.3 times 8. 8, 24, 10.4 minus 8. 10.32, I think. But no, that might be right. Let's see. Is it? Okay. We'll add them up. 8, 8, 28.88.
Yep.
And then we'll do the other one. So on this side, we've got 4-inch times 5, or 4 feet. I'm sorry, 4 feet. No. One more time here. We've got 4.38 for the 4-inch. And for the 6-inch, we've got 0.61. Okay. Four-inch times 5, that times 10, so we get 6.10, 21.9, okay. So here we get 28 flat, is that it? Okay. There we go. Are those pretty close, eh?
Yeah.
Now, our charts are going on every 20 gallons per minute, okay? I don't think we're going to do too much better than that. We're in the 800s. Given the fact that our chart only lists every increments on 20 gallons per minute, I don't think we're going to get too much closer than that. And keep in mind, these charts aren't perfectly accurate anyway, so I think I'd be pretty comfortable saying 300 gallons per minute is going to go on the AD side. I'm sorry, 300 gallons per minute this way, and then 200 going the other way. Okay, we've got questions on that? We good? Oh, okay. So that's about it. Okay, that's now. Keep in mind, if you have something like the city of Albany, where you got all these residential neighborhoods and intersections and pipe looping going all over the place, it's going to be a very complex process. But it's the same idea. And I don't think we really want to belabor this, too much. I just want you to understand the basic idea of how you would analyze the system. Okay. So we got any questions on that? All right. Yeah. So that's the basics of that. The whole idea is to balance out the head loss. That's the whole idea on that. All right.